In this next example, we revisit a problem that's very similar to the problems we worked out in the last lesson. And here in part A, I've worked out the average rate of change on the interval -1 to 1. And that average rate of change is equal to 0. Now we're going to find f prime of 0. And as we know, I'm actually going to change things up just for the purpose of this problem. I'm going to use the alternate definition. So we're going to take the limit as x approaches a, in this case x approaches 0, of the f of x minus f of a, or f of 0, all over x minus 0. Okay, continuing this on, try to make this as quick as possible. This comes out to be x to the 2/3 minus 0 over x minus 0. And obviously those zeros contribute nothing to both the numerator and denominator. And I'm going to simplify x to the 2/3 over x, and that comes out to be 1 over x to the 1/3. And as you should see or know, this does not exist. Okay, so we know it doesn't have a derivative, but I would like you to notice, just for some detail in helping us classify here, if I take the limit as x approaches 0 from the right of 1 over x to the 1/3, well, as I'm getting closer to 0, I'm coming from the right, so those are positive numbers, so this fraction will continue to grow without bound, and so this is technically approaching positive infinity. That doesn't exist, it's just getting larger without bound. And if I go down here and do the limit as x approaches 0 from the left of 1 over x to the 1/3, well, then we are still getting closer to 0 in the denominator, but those numbers are negative, so this is going to approach negative infinity. This simplification is not the function itself, this is the difference quotient. So the difference quotient is approaching either infinity or negative infinity, depending on the direction, and so that helps us to classify the type or reason that this function is not differentiable. This math tells us that f has a cusp at x equals 0. So f does not have a derivative, does not have a slope at x equals 0. We would say that f is not differentiable at x equals 0. If we look at the original function's graph, then this graph would come down like this and come up like this, which is the classic cusp, no derivative at that sharp extreme corner. And of course, we would say in part C, there is no tangent line to f at x equals 0. There's no unique tangent line, and so for short, we say there is no tangent line. In this next example, we're going to prove a couple things, but I want to notice before we do this problem, I've gone over here and drawn the function p of x. You can see right away that this function is not continuous at x equals 1. And since it's not continuous, we know that it's not differentiable. But what I want to do is work through the math that shows us what happens in this case when something is not continuous. What happens in the derivative portion of this? So we're trying to find p prime of 1. Let's pretend we don't know that it's not continuous. And this is going to be the limit as h goes to 0, p of 1 plus h minus p of 1 all over h. And this is the same math we did before, and I'll put a question mark. And because of the piecewise nature, we need the two one-sided derivatives. So p prime from the right of 1 is the limit as h approaches 0 from the right. This should be more familiar to you, having practiced the homework problems. And let's just keep it going here. This is the limit as h goes to 0 from the right. We have 2, 1 plus h minus, I'm going to highlight this in pink, the value of the function at 1, and that's going to be 2, all over h. Okay, so when we work this out, this works out pretty similarly to what we've done before. What do we have? 2h over h, which is the limit as h approaches 0 from the right of simply 2. Limit of a constant is constant. So this number here is the number 2, and that makes great sense because the slope as we approach from the right is equal to 2. I'm going to give you a preview on this. It appears as though if we look from the left, highlighting the graph, it looks like the slope is going to approach 1. But this is not a corner, and so the number will not come out to be 1. This open circle here is going to create a little bit of havoc. The discontinuity is going to create a interesting math that lets us know that something happened there, that it's not in fact a corner. So let's go p prime from the left of 1, and I'll try to work this out as quickly as I can. H approaches 0 from the left, p of 1 plus h minus p of 1 all over h, which is the limit as h approaches 0 from the left. Okay, now here's where we get to the nitty-gritty. P of 1 plus h to the left is going to be 1 plus h plus 3. And then I have to subtract p at 1, but I highlighted that earlier in pink to emphasize that p at 1 is in fact this pink value of 2. And this is all over h. Now here's where the math is going to get a little bit interesting. So this is going to be the limit as h approaches 0 from the left. This is going to end up simplifying to be 2 plus h over h. And I'm going to write this as the sum of limits. So this is the limit as h goes to 0 from the left of 2 over h plus the limit as h approaches 0 of h over h. Now to get to the important part, I'm just going to rewrite this. H approaches 0 from the left, 2 over h plus the limit as h approaches 0 from the left of 1. So we know for a fact that this part is going to equal 1, but this portion here is not defined. That limit is negative infinity, and the negative infinity is not important. What is important is the fact that this limit does not exist. See, the reason that the slope has here as we approach is not equal to 1 is because this point here in pink sort of threw it out of whack, and therefore we get a limit of the difference quotient. The slope is undefined as we come in from that direction. So the slope is 1 as we get close, but at this point here we say that the function does not have a derivative. And we conclude the way we've been concluding all along. This doesn't exist. We say, therefore, p is not differentiable at x equals 1. In part B, we say p is not continuous. This is our classification at x equals 1. So we see that when p is not continuous, p cannot be differentiable. In part C, they want a formal proof for whether or not p was continuous at x equals 1. In fact, had we done part C first, we would not have had to do part A, and I'll explain here in a moment. So this is just a good old review. P of 1 is equal to 2 times 1, which is equal to 2. In step 2, we find the limit. Since it approaches piecewise, we are doing 2 different limits. Okay, and so this limit as x approaches 1 from the right of 2x is equal to 2. Remember, in the continuity proof, you're doing limit of the function. You're not doing the limit of the difference quotient. It's sort of simpler when we just do continuity. Limit as x approaches 1 from the left. The behavior to the left was x plus 3. And so that comes out to be 4. So first thing I want to conclude locally is that the limit as x approaches 1 of p of x does not exist. Then in step 3, I talk about continuity. I say that this limit as x approaches 1 of p of x does not equal p of 1, and therefore, I ran out of room at the bottom, therefore p is not continuous at x equals 1. So even in a formal proof situation, if you find that a function is not continuous at x equals a, you can automatically state that the function is not differentiable at x equals a without any limit of a difference quotient, without any derivative definition. Let's switch gears here for a moment. We're going to talk about logic. Consider a statement, and we're going to assume that this statement is true. The W will stand for you win the calculus tournament. And if you win the calculus tournament, you will get a trophy. Let's assume that this original statement is true, and by the way, it is true. If you win the calculus tournament, you will earn a trophy. Let's talk about some logic statements. What is the converse of this statement? If you recall, the converse says, if I've earned a trophy, that implies that I've won the calculus tournament. Is that true? No, that's not always true. That's not logically equivalent to the original statement. See, sometimes I give out second place trophies. Sometimes I give out sportsmanship trophies. So in that case, winning a trophy does not imply that you won the calculus tournament. Let's go back to the original statement here, and let's talk about the inverse of this statement. The inverse of this statement is if I do not win the calculus tournament, that means I will not win a trophy. That is also not logically equivalent. That's just not true. If you don't win the calculus tournament, you still might earn a trophy in my class. So that does not imply that you will not win a trophy. The only thing that is logically equivalent to the original statement is the thing we call the contrapositive. And that goes, if we don't win a trophy, that implies that I did not win the calculus tournament. And that absolutely is true. If you come from my class and you haven't earned a trophy, that certainly means you did not win first place in the calculus tournament. So the two statements that I have boxes and stars around, those are logical equivalents of one another. And so what does this mean for calculus? Well, we've discussed a couple times that if a function is not continuous at x equals a, that will imply that the function is not differentiable at x equals a. And I would like to prove that statement. In order to prove that statement, I'm going to look at its logical equivalent. I'm going to look at the contrapositive. I'm going to say that if a function is differentiable at x equals a, then that will imply that the function is continuous. And so proving this statement here will be the same as proving this, and we can say that both of these theorems are true by providing the proof for one. So here goes a very important theorem. If a function f is differentiable at x equals a, then it is true that the function f is continuous at x equals a. That's going to be our proof. Now, I don't know how much you've learned about proofs. In an if-then proof, you start off with the if portion. You assume that the if portion is true, and then you use anything you can, theorems, definitions, to see if it logically concludes the then portion. So in an if-then proof, we're going to assume that f is differentiable at x equals a. So what does that mean? I know then that that is a case. I know that that is true. So what does it mean that f is differentiable at x equals a? Well, we have two definitions for that. One's the standard, one's the alternative. I'm going to use the alternative here. I'm going to say the limit as x approaches a of f of x minus f of a all over x minus a. We know that that exists. I know that that exists, or I assume that that exists, because that's the hypothesis or if portion of our theorem. And so now we want to show, this is the burden of proof, we want to show that f is continuous at x equals a. Now, what does that mean for a function to be continuous? Well, we've dealt with this at length. That means that the limit as x approaches a of f of x equals f at a. So assuming the pink should lead to the green. So now let's begin our proof. Let's start off by saying that f of x is equal to f of x, and that's going to be a true statement. Next, I'm going to say that f of x is equal to f of x minus f of a. Wait a minute, that's not always true. That's not fair. We can't say that that is true. One way to make that true is to add f of a here. So this is what I have coined 0 in disguise. These two together go to 0, so it doesn't change the original equivalent statement. Let's continue from here. Next, I'm going to say that f of x is equal to f of x minus f of a over x minus a plus f of a. That's not necessarily true. In order to make it true, I'm going to multiply x minus a so that we have what I like to call 1 in disguise. See, this quantity here will cancel out with this quantity here, making this statement the same as the original statement. I am next going to take the limit of the statement. I'm going to take the limit of both sides. I'm going to take the limit as x approaches a of the left-hand side, and that will equal the limit of the right-hand side. Now, on the right-hand side, I'm going to employ properties like the limit of a product is product of limits, and limit of a sum is sum of limits. So essentially, I'm distributing this limit statement to a couple of the expressions, and it will apply to this expression times the limit as x approaches a of this expression plus the limit as x approaches a of the final expression. Left-hand side is the limit as x approaches a of f of x. This is the awesome portion. How do I know that this exists? What gives me that information? Well, if I come over here to the top, I know that that is true because I assumed that that limit of that difference quotient exists, so I know that this exists. And since I know that it exists, I'm going to give it a name. I'm going to call it f prime at a. Its existence is the important part here. Next, I want to look at this portion of the limit, and as x is approaching a, I can substitute a in for x, and that gives me the value of 0. Plus, now f of a itself, this is not a variable, this is some constant. F of 2, for instance, might be 7, so this thing in the pink box is just a constant, and the limit of a constant is the constant itself, so this comes out to be f of a. So we see here that starting off with f of x equals f of x and using some given information, I lead to the limit as x approaches a of f of x equals f of a. That you should see as the definition for a function being continuous at x equals a. And so therefore, f is continuous at x equals a. This was the definition for continuous at x equals a. Pretty cool, right? That deserves a smiley face.